asphalt shingle is less than 1/4 of an inch thick. Yet it can protect one of your most valuable assets from the full force of nature. This is far more than a simple piece of roofing material. It is the result of advanced materials engineering, combining refined asphalt, reinforced fiberglass, and specially engineered mineral granules designed to resist fire, weather, and UV radiation. These components transform what appears to be a simple product into a durable protective barrier capable of shielding a home for decades. Today, join Factron Process as we go inside the production line and uncover the technology behind the roofing material that has come to dominate rooftops around the world. Before the 20th century, wooden roofs were one of the reasons urban fires could spread so rapidly across American cities. Asphalt shingles were developed not just to keep out rain and sunlight, but as a practical fire-resistant building material. Their introduction helped bring an end to the era of highly flammable roofs, turning homes from potential fire hazards into far safer structures capable of resisting one of the most destructive threats to any community. Today, asphalt shingles have grown into a massive industry with a global market valued at nearly $15 billion. More than 250 million squares are produced each year, enough to cover the roofs of millions of homes around the world. In the United States, they remain the most widely used residential roofing material. North America stands at the center of this industry, accounting for nearly half of global demand and serving as the heartland of asphalt shingle production and consumption. Before an asphalt shingle can withstand sunlight, repel rain, and remain firmly attached to a roof for decades, its journey begins by transforming solid rock into a stream of molten glass. At silica sandstone quarries, engineers drill blast holes according to carefully calculated patterns before carrying out controlled explosions to break apart dense layers of silica-rich rock deep within the deposit. Hydraulic excavators then move in, with each bucket capable of lifting up to 22 short tons of rock and loading it into mining trucks carrying between 55 and 65 short tons. The sandstone is transported to a jaw crusher, where it is reduced to pieces roughly 2 to 4 inches in size. It then passes through multi-deck vibrating screens and high-pressure washing systems operating at between 75 and 115 pounds per square inch to remove mineral dust, clay, and other impurities. The purified silica is blended with finely ground limestone, soda ash, and various additives before entering a continuous melting furnace. Inside, temperatures rise from approximately 1,832 degrees Fahrenheit to more than 2,822 degrees Fahrenheit, and the material remains in a molten state for nearly 50 hours until the glass becomes fully homogenized, free of trapped gases, and ready to be drawn into fiberglass fibers. From the distribution forehearths, the molten glass enters one of the most sophisticated stages of the entire production line: fiberglass fiber drawing. Instead of being cast into solid forms, the glass is directed through highly precise bushings made from platinum rhodium alloy, a material capable of maintaining extremely stable opening dimensions while operating under intense heat for long periods of time. In modern systems, each bushing can contain anywhere from several hundred to nearly 10,000 microscopic openings, continuously dividing the molten glass into countless fine filaments. Below, high-speed winding equipment rotates at roughly 3,000 revolutions per minute, pulling the glass into fibers only a few micrometers thick. For comparison, the average human hair is about 70 micrometers in diameter, while these fiberglass filaments measure only a small fraction of that size. Almost immediately afterward, low-pressure water sprays cool the fibers within moments of formation. A specialized chemical coating is then applied to improve bonding performance and reduce static electricity buildup. These fiberglass fibers will eventually form the structural reinforcement layer that prevents asphalt shingles from tearing, warping, or cracking after years of exposure to the elements. From the fiber drawing stage, the ultrafine glass filaments enter a high-speed winding system. Here, maintaining the correct tension is critical. Ceramic-coated guide rollers keep each filament under carefully controlled tension. Too little, and the fibers can become tangled. Too much, and they can break instantly. Highly sensitive sensors continuously monitor the process, while servo-driven motors guide the fibers onto winding drums with remarkable precision. Layer after layer, the filaments are wound into uniform rolls without gaps or overlaps. The result is a series of neatly organized fiberglass spools that resemble giant industrial thread rolls. Although lightweight, these fibers will eventually become the structural reinforcement layer that gives asphalt shingles the strength to resist tearing, warping, and years of exposure to harsh weather conditions. From the completed fiberglass spools, hundreds of bundles are fed simultaneously into high-speed rotary cutters, where they are chopped into short strands, measuring roughly 1 to 2 inches in length. Compressed air then blows these fibers onto a moving conveyor. Unlike traditional woven fabrics, which require fibers to be aligned in a single direction, fiberglass mats for asphalt shingles are intentionally formed with fibers distributed randomly across the entire surface. Once the fibers have been evenly distributed, the mat passes through a binder application zone, where a fine mist of phenolic or acrylic resin is sprayed onto the surface. Only a tiny amount is needed to bond the fibers together without making the material overly rigid. The mat then enters a multi-stage curing oven, where hot air ranging from 390 to 480 degrees Fahrenheit hardens the resin and locks the entire structure into place. By the time it leaves the production line, the fiberglass mat has become a fully formed reinforcement layer, ready to serve as the structural backbone of an asphalt shingle. How can a roofing material remain waterproof for decades without softening under the summer sun or becoming brittle during the winter? The answer lies in the asphalt layer that provides the roof's primary water-resistant barrier. Although it originates from petroleum bitumen, roofing asphalt is not the same material used in conventional road paving. In modern manufacturing facilities, bitumen is pumped into large heated storage tanks and maintained at temperatures between 350 and 400 degrees Fahrenheit before entering the oxidation process. During this stage, air is continuously blown through the hot asphalt, introducing oxygen that alters its internal structure. This increases the material's softening point, making it harder, more stable, and better able to withstand the extreme temperatures encountered on a rooftop. Not all of the asphalt comes directly from newly refined petroleum. In many facilities, a portion of the raw material is recovered from reclaimed pavement. After crushing, screening, and refining, the remaining usable bitumen is returned to the production process and given a new life. To further improve performance, some formulations incorporate SBS polymers, which enhance flexibility and elasticity. This allows shingles to resist cracking as they repeatedly expand in the heat of the day and contract during cooler nights. The result is a waterproof protective layer that is rigid enough to endure years of heat exposure, yet flexible enough to protect a roof reliably for decades. If asphalt serves as the waterproof armor of a roof, then the mineral granules on its surface act as its shield against harsh ultraviolet radiation. A single asphalt shingle roof can contain billions of tiny ceramic-coated stone granules. These particles do far more than provide color. They function as sunscreen, fire protection, and a defensive layer that protects the entire roofing system. Without them, the lifespan of a roof could be reduced from decades to only a fraction of that time. To create this protective layer, the salt or granite is crushed into particles ranging from approximately 0.016 to 0.067 inches in size. The granules are then washed, dried, and screened to ensure a uniform particle size. Next, each granule receives a thin ceramic coating through a high-temperature process that bonds metal oxides to its surface. This coating not only locks in color for years, but also produces a wide range of shades, including gray, red, green, and brown, allowing asphalt shingles to complement many different architectural styles. Once they enter the production line, the granules are evenly distributed across the hot asphalt surface and pressed firmly into place by heavy rollers. Although they may appear simple, these tiny particles help roofs retain their color for decades, reduce heat absorption, and protect the asphalt beneath from continuous aging caused by sunlight and weather exposure. After the mineral granules are applied, the hot roofing sheet moves into a cooling system. Large axial fans blow cool air across both sides of the material, gradually lowering its temperature and preventing cracks caused by sudden cooling. Beneath the conveyor, water-cooled rollers continue removing heat while helping keep the sheet flat and stable. At the same time, infrared sensors scan the surface in real time to monitor temperature and coating quality. If the system detects soft asphalt or an uneven surface, the defective section is automatically flagged and removed before it can move further down the line. By the end of this stage, the material has cooled, stabilized, and is ready for the final cutting process. Once the roofing sheet has reached a stable temperature, it moves directly to the automated cutting station. Here, razor-sharp tungsten carbide blades operate at high speed, slicing the continuous asphalt sheet into standard shingles measuring approximately 39 by 13 inches. The key to this process is synchronization. Servo motors and digital encoders continuously match the cutting speed to the movement of the conveyor, maintaining an exceptionally tight tolerance of just plus or minus 0.012 inch. Equally important, virtually nothing goes to waste. Trim edges and defective products are collected, remelted, and fed back into the production process, creating a highly efficient closed-loop manufacturing system with minimal material loss. Immediately after cutting, the asphalt shingles enter the final inspection line. As they move along the conveyor, technicians continuously monitor the dimensions, shape, and surface quality of each shingle. Defects such as uneven cuts, poor mineral granule adhesion, or surface imperfections can cause a product to be rejected. Any shingles that fail to meet specifications are automatically separated from the line and sent for recycling. Random samples are routinely sent to the laboratory for further testing. Engineers evaluate tensile strength, water resistance, and long-term UV durability. Every result is recorded and linked to a specific production batch for traceability. This serves as the final quality checkpoint before the shingles are cleared for packaging and distribution. After passing inspection, the shingles move into a semi-automated packaging line. Along the conveyor, the shingles are automatically stacked into bundles containing between 18 and 22 pieces, depending on the product line. Next, high-speed wrapping machines apply heat-resistant plastic film around the bundles, while heat-sealing units secure the packaging to withstand handling and transportation. Each bundle receives a unique QR code that stores information ranging from its production batch to its shipping date, providing full traceability throughout the supply chain. Finally, the packaged bundles are arranged onto pallets according to optimized weight distribution patterns. Forklifts then transport the pallets into storage warehouses where they await shipment before beginning their journey to rooftops across the United States. After spending 20 to 30 years protecting homes from heat, snow, and hail, asphalt shingles eventually reach the end of their service life. The asphalt ages, protective granules begin to wear away, and the material gradually becomes brittle and prone to cracking. Each year, more than 10 million tons of old shingles are removed from roofs across the United States. What makes this especially striking is that while these products are designed to withstand decades of weather exposure, they can take centuries to break down after disposal. And although the industry continues to expand its recycling efforts, most discarded shingles still do not make their way back into the manufacturing cycle. That raises an important question. Will the future of roofing be defined by durability alone, or by the ability to be reborn after its job is done? To keep old shingles from spending centuries in landfills, they are collected and transported to specialized recycling facilities. There, truckloads of roofing waste are unloaded onto conveyors, where the recycling journey begins. Powerful magnetic separators continuously remove nails, screws, and other metal debris, while sorting systems separate plastic, wood, and additional construction waste from the material stream. The shingles are fed into industrial shredders. Large steel cutters tear through the aging roofing material, reducing it into small black granules. This process recovers valuable asphalt and mineral content that still remains inside the shingles, allowing those materials to be reused in new applications instead of becoming permanent waste. Today, most recycled shingles are used in road construction. The processed material is blended into hot mix asphalt, replacing a portion of virgin asphalt in aggregate while reducing costs and conserving resources. However, the recycled content is typically limited to about 3% to 5%, since excessive fiberglass can make pavement brittle and more prone to cracking. Technologies designed to turn old shingles into new ones are still being developed and currently handle only a small fraction of the millions of tons of roofing waste generated each year. And with that, the journey of asphalt shingles, from the factory floor to rooftops and even highways, comes to an end. Behind their widespread use lies an industrial system built on remarkable precision, one that not only protects millions of homes, but also reflects the growing ambition of a more circular materials economy. Yet an important question remains: will asphalt shingles continue to dominate the roofing industry as material technologies evolve at an ever-increasing pace? And what new capabilities might the roofs of the future possess? The answers are still being written, and they may be closer than we think.